Hello! In this video, we present a brief introduction to the synthesis of three drugs used in the treatment of various types of cancer: Futibatinib, Erdafitinib, and Pemigatinib. The series includes an introductory video, this video, videos on retrosynthesis, and on the resulting syntheses. Shown here are the systematic name, the 2- and 3-dimensional structures, and the chemical abstract service number for Erdafitinib, as well as its main structural features. Here, the same type of information is shown for Pemigatinib. Here, the same type of information is shown for Futibatinib. We can visualize the structural evolution of Erdafitinib as the modification of the benzopyrazine heterocycle, also known as quinoxylene, to which various groups were added, such as the amino group in compound 1 and the heterocycle of methylpyrazole in compound 2, to optimize the pharmacological and pharmacokinetic properties until reaching Erdafitinib. Pemigatinib is based on compound 1 as a precursor, which was modified by replacing the proliferimidine heterocycle with a prolipyridine, as in compound 2. In compound 3, a cyclic urea was formed to obtain a fused tricyclic structure that was optimized until reaching Pemigatinib. Futibatinib is based on compound 1, which features a pyrimidine pyrrole heterocycle, which was replaced by a heterocycle of pyrimidine pyrazole, as in compound 2. Additionally, the quinoline substituent was replaced by a chain formed by a triple bond and a dimethoxyphenyl group. All three drugs are inhibitors of the fibroblast growth factor receptors, FGFRs, which, when they undergo genetic alterations, stimulate the proliferation, survival, and spread of cancer cells. Erdafitinib and Pemigatinib are reversible inhibitors, while Futibatinib is an irreversible inhibitor. Futibatinib is an irreversible inhibitor because it has an acrylamide group, a highly reactive electrophilic group susceptible to attack by nucleophilic groups like the sulfhydryl group. Of the amino acid cysteine, amino acid present in the receptor structure, which can react with the acrylamide group through a Michael-type reaction, thus forming a covalent bond with the receptor. Regarding the structure-activity relationships of Erdafitinib, we can say that it is characterized by having a molecular scaffold of quinoxylene, a bicycle formed by a pyrazine heterocycle fused to a benzene ring, which forms crucial hydrogen bonds to bind the drug to the receptor's active site. Its substituents help optimize affinity for the receptor and its pharmacokinetic properties. Regarding the structure-activity relationships of Pemigatinib, we can say that it is characterized by having a pyrrolopyridine as a molecular scaffold, which is a bicycle formed by a pyrrole ring fused to a pyridine, which forms critical hydrogen bonds with the receptor. Its substituents contribute to optimizing its selectivity and its pharmacokinetic properties. Regarding the structure-activity relationships of Futibatinib, the acrylamide group stands out, which, as previously mentioned, is an electrophilic reactive group, which reacts with cysteine residues in the receptors, forming covalent bonds. Other groups present in the drug, such as pyrrolidine, Project, and Orient, the acrylamide group to facilitate the reaction with cysteine 491, as in the case of the receptor FGFR2. Also notable is the bicycle formed by the pyrazole ring fused to a pyrimidine, which determines the drug's orientation and its interactions in the active site. The three drugs were patented in the second decade of this century. Erdafitinib was approved in the United States in 2019. Pemigatinib was also approved in the United States in 2019, and Futibatinib in 2022. The three drugs are indicated for the treatment of various types of cancer. Here are some pharmacokinetic and adverse reaction data. Notably, these drugs can be administered orally. Here are some relevant physicochemical properties. The resulting retrosynthesis and synthesis will be presented in the following videos. Thank you for your attention.